All right, so chapter 16, sapling. This is like number 4. This is actually very similar to the one we did in the workshop. Actually, I think I stole this and put it on the workshop. And it's a 1-to-1, so 1 mole to 1 mole ratio. And they ask you, after the reaction is complete, what species can be found in the mixture? So, acid chloride is pretty reactive, right? So it's certainly going to react due to addition. O minus Cl. Right, so this is I would call this a neutral reaction conditions, right, to start off with. We're not strong acid or strong base, it's neutral. So we have no charge to start off with, so we better have no charge ever, right, overall. So we've balanced our minus and our plus charge. So we can do a proton transfer here. Right, because once we have a tetrahedral intermediate, we always want to collapse it and do the elimination. We always eliminate the best leaving group, and right now the best leaving group would be this amine part, which we just added, which would make no sense going backwards. But now chlorine, right, can't take the H. O minus is the most electronegative. So when we say proton transfer, this H is going to end up on that O. Now we're back to neutral conditions. Good. Now with the tetrahedral intermediate, what's our best leaving group? I would say our best leaving group is the chlorine, right? And so let's have the oxygen's electrons come down and kick out the chlorine. So what did that make us? All right, plus Cl minus. So at this point, the Cl minus is going to, of course, take the H. So what we're going to have is the amide, the product we expect. We also made HCl. And this is where the problem is, right? We made HCl. HCl is what? It's a strong acid. So if we have a strong acid around and we have an amine, what do you think the amine is going to react with first? Is the amine going to react with the strong acid, or is it going to react with the carbon of the carbonyl group? The acid. Right? So what's going to happen then is any leftover amine is not going to react with the carbonyl carbon. It's going to react with the acid. And so what they're looking for here, and I had it on the solutions manual too, is essentially drawing leftover starting material, the amine, right? So imagine if there's any more amine around, right? It's going to react with the HCl because the HCl is so much more delta plus than just the carbon of the carbonyl. And at that point, what's going to happen? Okay. Right, you're going to make the amine, but the protonated version. So this problem, what they're looking for is they're looking for this, the product. They're looking for this protonated amine and also leftover acid chloride. Those are the 3 things they're looking for. So let's say another way to think about it. So if you had 100 of each of these, 100 of acid chloride and amine. So let's say 50 of them, or 50 of them react like this. Then you're also going to make 50, every time this reaction, you're going to make 50 HCl's. And every one of those HCl's is going to react with an amine before the amine can react with that. So the highest yield you can get is 50% of this product. So you'd have leftover acid chloride otherwise. So I forgot to record that, my bad. Carboxylate, acid chloride, top of Mount Carbonyl, tetrahedral intermediate. Ask yourself, what's the best leaving group? Chlorine is a better leaving group than a carboxylate anion, right? This is a more reactive species than Cl minus, so that's why it goes forward. Once you get the tetrahedral intermediate, you do the elimination, kick out the chlorine, and you make an anhydride, which of course is lower on Mount Carbonyl than is the acid chloride. Boom. Number 14. and they're putting in this anhydride. They're saying there's only one equivalent of that. Right, so it's a 1-to-1 ratio. So we have an anhydride, and we have this phenol and amine. Right, both a phenol and amine. So the anhydride is going to be what in this reaction? The electrophile or the nucleophile? It's carbonyl. Where are the carbonyls always been so far? At the end of the day, they end up being the electrophile, right? Which part? The carbon of the carbonyl, right? So that would be probably this. I mean, it doesn't matter which one you pick. Let's pick this one. So that means what if this is going to be my electrophile? That carbon is going to be my electrophile. What's this going to be? That's going to be the nucleophile. Now we have to choose. Which one's going to be which part's going to be the nucleophile? We have the lone pairs on the oxygen is one option. The lone pairs on the nitrogen is another option. Heck, you could even say the benzene ring. We could do electrophilic aromatic substitution. But that's probably not very likely, right? Because that would break aromaticity. So that's not as likely. So it's between the oxygen lone pairs and the nitrogen lone pairs. What say you? Who's more willing? Let's look at the periodic table. So what's different between nitrogen and oxygen? Oxygen's more electronegative. It's farther right in the periodic table. Okay? So which one do you think is more likely to react with its lone pairs? Oxygen or nitrogen? Nitrogen. Oxygen's more electronegative. Nitrogen's less. It's going to be less likely to hold on to those lone pairs. So we do the addition step. O minus plus. You know, numbering carbons would be a good thing here, right? You don't want to lose carbons now. You're getting this far. Do a little proton transfer. Well, I don't want to do it. Do it there. That's fine. OH is just kind of hanging out. New nitrogen carbon bond. OH. So now we have a tetrahedral intermediate with a balanced charge. All right, so we had tetrahedral intermediate here. We just had to move a proton transfer around. Now at this point, we got to figure out what our best leaving group is. Technically, our best leaving group is going to be this carboxylate. So this time I'm going to take the OH electrons, have those go. And what that's going to give us is we regenerated H+. OH. Now we have an NH. I lost the methyl. There's a methyl there. There's a methyl there. There's a methyl there. Don't lose a carbon. That's why I said number them, right? Ooh. Right? So there's a methyl there in that tetrahedral intermediate the whole time. I lost track of this guy. He was there. And the other byproduct is the carboxylate, which is stable because of resonance. So those are your two that's your product. All right, looking at number 15. So the cyclic amide, we call these lactams. And in this case, so we know amides are pretty strong, right? Pretty strong bonds. This is a 5-member ring, which is fair. It's not like penicillin before, which are much more reactive, right? So 5-member rings are fine. So we're using H+, water, and heat, right? So amides are on the bottom of Mount Carbonyl, but if you start putting H+ and heat going on in there, they're going to react. So the first step, right, we need to make this carbon and the carbonyl more reactive. It's not very delta plus right now because of so much resonance, right? And this is not a very good leaving group either. So one of the ways we can make it more reactive is by protonating it. So now by protonating it, what we've done, right, we made this carbon and the carbonyl that much more delta plus, right? That's one of the two things we ask ourselves when we're running about reactivity. How good a leaving group does it have, and then how delta plus is this carbon with this carbonyl? So now we've made this carbon that much more electrophilic, delta plus. So now water can come along and act like a nucleophile and do that addition step. Now notice, balance my charge, overall plus charge, we're in acidic conditions here. So make sure you never have O minus around, right? If you're in acidic conditions, you can't have O minus. Saw a lot of that in some of the old tests. Don't mix genres. Acids and bases react with each other. So if you have an H plus and an O minus around, they're not going to react with something else, they're going to react with each other. So at this point, tetrahedral intermediate, the best leaving group though is what? What's the best leaving group here? Water. That's what we just added, right? So we need to do a proton transfer to get, right, that H someplace else. If you look at this, you should have started out thinking, right, this is the bond we're going to break always. Right, whenever you see these, you start saying the amide bond is going to break. That's the bond we're going to break. So I need to make this into a better leaving group, right? Just like we added the H plus to make this more delta plus. Now once you get to this point, you need to make the leaving group better. So the way to make this a better leaving group is to do what? Give it a plus charge, right? And the way I can do that is by having it have a hydrogen, right? Go after the hydrogen. Doing a proton transfer. So a little PT. OH. OH. So now it's a better leaving group, right? So what's going to happen now, I'm going to have the OH electrons come down. We'll make H plus that way. Kick out the nitrogen, the best leaving group. So now I have a carboxylic acid. I made H plus, right? This hydrogen right here is this hydrogen. This hydrogen is this hydrogen. Right? I also have, careful not to lose a carbon, the amine, right? So very similar to what we saw before, I have a carboxylic acid and amine, and I have H plus. Well, don't forget, amines are also good bases. That H plus is going to react with the amine. So that nitrogen is going to take that H plus, right? Because that nitrogen doesn't have a full, the hydrogen doesn't have a full octet right now. So why would it react, right? It doesn't have a full, we call it a duet. Because hydrogen only can handle 2 electrons, so they call it a duet. That makes sense. I always thought that was funny. Right? Because we always want things to have full octets or duets. So this is what the final product looks like. This says everybody has full octets. Because H plus itself, by itself, doesn't have a full duet, as it were. So that's why the nitrogen will protonate first. So that's the actual answer. So number 26 is an interesting one. It says, propose a structure for compound A, that's blank. It has an IR spectrum at 1820. Whoa. And a single proton NMR absorption at 1.5 ppm. So just one NMR peak at 1.5. It says compound A reacts with water to give dimethyl malonic acid and with methanol to give monomethyl ester of the same acid. So Compound A was unknown until its preparation in 1978 by chemists at the University of California, San Diego. UC San Diego. Cool spot. So let's look up with dimethyl malonic acid. So that would be the Google would help you with that, but I can show it to you too. It's cool. It's actually used sometimes used as a chiral catalyst. Some C2 symmetry, but that's a whole other discussion for another day. So they're saying this is dimethyl malonic acid. And they're saying compound A reacts with water to give this. All right? So compound A makes this with water. If you have water, compound A turns into that. And it also reacts with methanol to give that. Okay. So what is our starting material? So if you reacted with water and you got a diacid, what kind of starting material did you start with? This is a tough one. So you've added water. Let's think about it that way. You've added water, right? This is adding water. Where is, if I labeled this oxygen at starred red, and these two hydrogens starred red, where are they at in the product?
One of the OHs.
There's the three elements from water there. So what was this have to be then?
An anhydride.
It had to have been an anhydride. And it's a weird looking anhydride because it's a 4-member ring anhydride. Right? It's the same here too. Right? So that's where that came from. That's one way to look at this, to analyze this. Right? You added water to it. Where's that water? Here, right? Where'd the methanol end up? Here's the OMe and there's the H, right? Where did it end up? So what's left over is that oxygen had to be bonded there as an anhydride. Now, back to the 1820 thing.
Yeah.
So IR, right? As you become more ring strained, think about what kind of vibrating, how much bending can you do or shaking. If you're in a ring, you're going to be a lot higher frequency, right? You're going to be a lot tighter. As your frequency got tighter, what happened to your wave number? It got higher. All right, remember that?
Yeah.
So there you go. He's just... All right, so this is number 29, so this is a good retrosynthetic problem. We're actually working on making a drug here. It's called Dilacetrib analog. So it's a cardiovascular disease fighting agent that inhibits cholesterol ester transfer protein. So it helps stop the increasing of HDLs, those bad cholesterols. HDLs are the bad ones. So I've been told. I am not a real doctor.
You mean LDLs?
LDLs are bad? HDLs?
HDLs are good.
HDLs are good?
Yeah.
High density? This is a recording. Alright, NH, let's just draw the thing. Okay. So if you look at this, let's look at things that we know how to make. Right? Things that we know how to make. So we know how to make amides. That'd be the first thing I'd look at, right? We know how to make amides. So we're really thinking about making this bond. This is the bond we're thinking about making. So amides we know are the bottom of Mount Carbonyl. If we look at what part is going to react with the amide, this is an amine. It's an aniline. And we should go back and think, well, do I know how to make an aniline? And hopefully somebody's like, yes, I do know how to make an aniline. Right? How do I make an aniline? Remember that came from maybe nitrobenzene. And maybe how do I make nitrobenzene? That comes from benzene. Yada, yada, yada. Right? So if I take one step back here, and now this is pretty tough. They do a little better job directing it. So this, I wouldn't expect you to like see all this right now, but what's the best thing I can react, right? If I really want to make sure this bond forms, what kind of carbonyl should I use to get that amine part to react with it? Acid chloride, right? Let's go to the top of Mount Carbonyl. Let's do the acid chloride. All right, very good. So now we got to figure out how to make, right? So our nucleophile is aniline. And way back when, you knew how to make this from benzene. Yeah. So one step back, this would have been nitrobenzene. And one step back from that, they actually tell you the first starting material is actually benzene. So that's working our way all the way back. Good. So now moving forward, how did I put an NO2 group on a benzene? What do I have to use? The HNO3 and H2SO4. Remember that was the one where somebody had to be the base? Right? Two strong acids, but sulfuric acid is even stronger. And now you knew a couple ways to do this. How did we reduce an NO2 to NH2? Palladium on carbon was one way. Palladium on carbon, then we had to have, obviously had H2 gas. Wasn't there another way I think I showed you?
You did.
That was one way. I think the other way was they use zinc or iron, actually, in this case will work. HCl will also reduce it.
Were those the only two?
Those are only two ways, yep. They want the iron one in this case. They want iron, HCl, and then base, and a base NaOH workup. And then from this point, this is just a matter of mixing this and this aniline together, right? Because this is so reactive that you don't need any catalyst to make an amide. It just happens. All right, looking at an NMR problem, NMR unknown. Obviously, it's going to involve carboxylic acid derivatives at some level. So we're thinking esters, amides, carboxylic acids, acid chlorides, anhydrides, things like that. Right? Otherwise, it wouldn't be in this chapter. So the IR tells us, so I'll do the IR first, even though I put NMR up there first. IR tells us we have at 3,000 to 3,580, a very broad peak. We also have one at 1698 and another one at 981. And at 981, if you took out your IR tables, which I know you carry everywhere, there it is, the 981 should tell you something very distinct. All right? What does it tell? What does the 981 tell you?
Double bonded C with an H bend on an alkene.
Does it tell you what kind of double bond C? Cis, trans, or neither?
It just shows double bonded C with an H.
Well, one of them,
It says bend and then alkene.
it would tell you it's a trans as well. So that would tell you it's trans, but we'd have another way in NMR to tell too.
Can I add that on the table?
Sure, it should be on the other. It's on the other table I always give you too.
That's always true.
Yeah.
It's also on my
Let's see. I'm not going to talk about the NMR yet. And then what about the 30? What do you think the 3,000, the 3,580 broad is? Big OH, probably. And then what about the 1698?
probably carbonyl.
Carbonyl. What kind of carbonyl though?
A weaker one? I don't know.
So the. Yep.
One that has some single bond character.
Single bond character. So it's going to be a carboxylic acid.
Yeah.
Right.
Why can't it be in a mid? Can't it technically?
It could be in a mid, but I'm going to tell you the mass spec is odd, so it can't have a single nitrogen in it.
How do you know when things are odd?
How do I know when things are odd?
You just said it was odd.
So there's the deal with, remember with mass spec, the nitrogen role?
Yeah.
Usually I'll give you the molecular formula.
Okay.
That's the way I like to do these problems usually. I give you the molecular formula. And then you figure out degrees of unsaturation and you do your thing, right? So in this case, let's pretend I gave you the molecular formula and your degrees of unsaturation is equal to 2. And your molecular formula is 1, 2, 3, 4, 5, 6. C6, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10, O2. So who can calculate the degrees of unsaturation for me? Okay, so I'd like to do this. Now we have the molecular formula. We've decided that there's a carbonyl. We've even decided that it's a carboxylic acid, probably. We decided there's an alkene. We decided it's trans. So let's go ahead and subtract those pieces out. So minus C for the carboxylic acid. O, oops, H, oops, H and an O, 2. So we're down to C5, H9, minus C2, H2 for the alkene. So we're down to C3, H7. That makes it a little easier. Now we look at the NMR. We haven't even looked at the NMR yet. And they do give you a mass spec too of 115, but I would usually just give you the molecular formula. So the mass and the NMR, it shows a peak at 11.9. That's way, way downfield. That should also confirm that's carboxylic acid. All right, that helps you know that. You see let's see, on the far right, you see a triplet with coupling constants at 7.4 hertz. That is worth 3 hydrogens, and that's at 0.9 ppm. So 3 H's, that's probably going to be what kind of function, what kind of group? It would probably be a methyl CH3. And it's a triplet, so how many nearest neighbors does it have? 2. So it's next to a CH2, right? So if this is A, we're calling these guys A. So we should be looking for, if this is B, how would B be split by A? B would be turned into what? A quartet, right? But I'm looking here and I don't have any quartets. I do have a 1, 2, 3, 4, 5, 6, a sextet. How many nearest neighbors does a sextet have? So hextet, sextet meaning 6 peaks. How many nearest neighbors would it have? 5. Well, HB is a sextet. So 3 nearest neighbors are A. And then on the other side, there must be HC, right? Another 2 protons. That makes sense? Right? HB is split into a sextet. That means it needs to have 5 nearest neighbors. Here's 3, here's 2. HA is a triplet. It means it has to have 2 nearest neighbors. Now HC is going to be split by HB how? Into what? How is HC going to be split by HB? Into a triplet. Now I don't see any triplets. That's because, right, now we're kind of stuck at this point, so HC looks kind of weird. Have we numbered down all our carbons? Have we got rid of all our carbons, these pieces? Right, C3H7 is gone, so we haven't missed anything. Now we have 3 pieces. How can we put them all together? There's only one way to do it, actually, and get everything in there.
So, how does HC split on those 3?
So I just didn't have room for it. So HC, pretend HC is bonded to HB. So there's a 3 carbon chain here. There's this trans alkene and this carboxylic acid. So how can I do this? How can I put it all together? There's only one way.
They'll all be coming out of
The carboxylic acid and this alkyl chain all come off the alkene. That's the only way it can work. So there's your final product. Let's do one more. Let's see how an anhydride reacts with two equivalences of diethylamine. Right? So an anhydride is more reactive, it's higher up Mount Carbonyl than an amide. So we're going to break this bond. Right? We're going to break at least one of these bonds to start off with. Right? That carbon's pretty delta plus. This is a pretty good leaving group. Nitrogen attacks. Right? We do our addition step. Are we in acidic, basic, or neutral conditions for this reaction? Acidic, basic, or neutral?
Are they supposed to tell us that?
I'm asking. Are we acidic, to start off with, are we acidic, basic, or neutral? It's neutral. Neutral. There's no strong base. There's no H plus. There's no O minus or anything like that, right? We're in neutral. Right? Now we make a charge in the second, after the first step we make a charge, but we're still overall net neutral, right? So we need to do, from this point, we need to do a proton transfer. So you can say there. And we know we want to break, right? We're always thinking about breaking this bond. This is our leaving group. We're going to break that bond right there. All right. Overall net neutral. We haven't gained or lost charge. So now what's our best leaving group? Right? We have a tetrahedral intermediate. What's our best leaving group here? What's going to be most happy with a negative charge? The carboxylate part, right? All right? Sweet. All right. So now what, though? So a carboxylate, we've basically said, is that reactive or not reactive? It's not reactive. Why? Because it has resonance, right? So is it going to be a very good base, a carboxylate? Is this O minus right here going to be a very good base? What is going to be a good base? Right, remember we had how many of these to start off with? 2. So what do you think is going to happen? The other amine is going to come swooping in. And take that H. So then what are we going to end up with? What's our final product going to look like? We're going to have made the amide. Yippee. We have the carboxylate. And then we have the protonated amine. The cool thing about this, anybody recognize this yet? This kind of form where there's a carboxylate,
Oh, amino acids.
amino acids. Yeah.
Oh, that's right.
Does sapling want both of those?
Sapling wants both of these, yes, with their charges. Oh, and it's NH3, my bad. Right, because there has to be, right, you start with NH2. So a lot of questions about, right, if you have a carboxylic acid, if you have an H plus around, have the amine react with it, right? That's going to be amine's going to be much more likely to react with that H as a base than it is necessarily react with the carbon of the carbonyl group. It's very similar to how amino acids behave. It's some pretty crucial stuff for life.